Hello, my name is Octavian Cornea. I am an associate professor at Politehnica University of Timișoara, Department of Electrical Engineering. Currently, my research is focused on modeling, simulation and control of power electronic converters in various applications, and especially DC-DC converters for energy conversion and storage. My teaching activity is related to subjects of power electronics, renewable energy, DC microgrids, and smart grids. I will present the fourth part of hybrid DC-DC converters, which is about an application of a unidirectional hybrid switched inductor DC-DC converter for a small power wind turbine energy conversion and storage system. The energy conversion and storage system for a small power wind turbine was implemented during the execution of the project. Improvement of the structures and efficiency of small horizontal axis wind generators with non-regulated blades, financed from EEA grants. 4 faculties from Politehnica University Timișoara were involved in the project: Faculty of Automation and Computer Science, Faculty of Electrical and Power Engineering, Faculty of Mechanical Engineering, and Faculty of Civil Engineering. This is the overview of the presentation. I will begin my presentation with a description of the wind energy conversion and storage system structure, WEX for short. I will show you how the components of the system are connected to form the system structure, and I will highlight the system operation in different scenarios. The basic characteristics of a wind turbine will be shortly presented because they are very important as a starting point of the chain of the wind energy conversion. I will show you the specific data of the 2 wind turbines that were used in the WEX implementation, one with 3 blades, the other one with 5 blades. A permanent magnet synchronous generator was designed for this application. I will give you its main characteristics. The unidirectional hybrid switched inductor DC-DC converter, HSI-DC for short, is at the core of the energy transfer from the wind turbine to the energy storage elements. Therefore, I will cover all the important aspects regarding its use in this specific application, which are steady-state analysis and theory of operation, stability analysis, which is very important in order to avoid electrical oscillations in operation, and experimental test results that proves the good operation of the converter and consequently the good operation of the system. 2 types of system control were being tested. A simple MPPT control based on the estimated characteristic of the maximum power in function of the rotation speed, and a fuzzy logic control, which is a more elaborate control method. I will shortly present both control strategies. The real operating conditions testing is discussed in another chapter. The conclusion chapter will summarize the benefits of the small power wind energy conversion and storage system presented. The objectives of this presentation are to present in a concise way the experience gained during the implementation of the research project focused on a small power wind energy conversion system, to provide advice on the complete analysis of unidirectional hybrid switched inductor DC-DC converter including stability analysis, to help researchers who may use a hybrid converter for similar applications, to show how system control can be easily implemented for a small power WEX, and generally to disseminate information that could be used for similar applications. The structure of the wind energy conversion and storage system was elaborated during the implementation of the research project, starting from the basic structure described in the project proposal. It suffered several stages of modifications and adjustments. The solution chosen for energy conversion in a wind turbine system depends on the nominal power. For high or very high power wind turbines at power level between 2 and 10 MW, a three-phase AC power converter is used to transfer the energy from the AC generator, which is mechanically coupled to the wind turbine shaft, to the AC grid. There is no energy storage in this case. For small power wind turbines, a different solution is possible. The AC power converter can be replaced by a DC-DC converter, simplifying the structure and reducing the total cost. In addition, the DC-DC converter can charge a storage element, a supercapacitor, or a rechargeable battery. In this way, this energy conversion solution could be used to supply DC loads and also to supply AC loads or to inject energy into the AC grid if an inverter is connected to the DC energy storage elements. In this slide, a simple block diagram of the small power WEX is presented. The small power wind turbine has a nominal power at the level of 5 to 6 kilowatts. A permanent magnet synchronous generator, PMSG, with three phases is used to transform the mechanical energy into electrical energy. A three-phase diode bridge is necessary to rectify the waveforms. A hybrid DC-DC converter is used to load the PMSG from maximum power point tracking operation. Different implementations are possible for the output side of the hybrid DC-DC converter, the load. In commercial wind turbines currently available at small power levels in the range of hundreds of watts or a few kilowatts, DC generators are also used, but we consider that for 5 kW and above, an AC generator is a better solution. This slide presents the wind energy conversion and storage structure with more details. A supercapacitor is used to store the energy provided by the electrical generator. The main advantage of the supercapacitor over the rechargeable battery is a much higher power density during charging and discharging. A battery is normally charged at a current of 1 per 10 of the capacity in amps hour, and this charging current can be adjusted during the charging process in function of the charging stage. On the other hand, a supercapacitor can be charged at the rated current for long time intervals, as long as the state of charge is below 100%. In other words, as long as the supercapacitor is able to store more electrical charge. Therefore, it will be no problem for a supercapacitor to handle the high power peaks from the wind turbine. Another important advantage of a supercapacitor is that its life expectancy is much higher than that of a battery. Its operation is guaranteed for a high or very high number of charging-discharging cycles. A life expectancy of more than 10 years is normal for a supercapacitor. On the other hand, the energy of the supercapacitor is increased by raising the voltage across the terminals, as for any capacitor. This means that the converter that deals with the supercapacitor charging has to be chosen to operate efficiently for a high voltage range at its output, where the supercapacitor is connected. This is the reason why a hybrid DC-DC converter is more suitable for this application than a standard or classical DC-DC converter. For example, when the supercapacitor energy is low, the voltage at its terminals is also low, and consequently, the input-to-output voltage ratio of the DC-DC converter is high. In this condition, a classical DC-DC converter operates at reduced efficiency, but a hybrid DC-DC converter performs without a significant decrease in efficiency. The charge controller uses the supercapacitor energy to charge the rechargeable battery BAT. A commercial inverter supplied by the battery is used to generate a local AC three-phase system to feed the AC loads or to inject the energy into the grid. The connection to the grid is optional. Of course, the system can operate in off-grid mode. Two resistors, R1 and R2, can be connected using two power switching devices, T1 and T2. R1, which is a three-phase resistor, can be connected at the PMSG output. R2 can be connected in parallel to the supercapacitor. These resistors are used for protection if the wind energy is in excess for a long time. Actually, there are additional loads that are needed only in the special case when the wind power is very high for extended time intervals. The energy storage elements are fully charged, and it is not possible to increase the power consumed by normal AC loads. In order to use the energy converted into heat in R1 and R2, in the simple scenario, they can be used for water heating. Only a part of the available energy of a wind turbine can be converted into electrical energy. There is a theoretical limit. The rotor blade of a wind turbine extracts the flow energy from air, converts it into rotational energy, and then delivers it to the generator for power conversion into electrical energy. The energy conversion process starts with the kinetic energy of an air mass traveling with a speed v, which is half of the product between the air mass and the airspeed squared. The air mass can be obtained if the blade swept area, the specific density of air, and the wind speed are known. The blade swept area is a constant that can be calculated from the blade geometry. The wind speed can have large, rapid variations, and the specific density of air is influenced by the temperature, pressure, and humidity of the surrounding atmosphere. The available wind power is equal to the derivative of kinetic air energy with respect to time. As this equation shows, if the specific density of the air is constant, the available wind power is a function of the third power of the wind speed. Two fixed-pitch wind turbines were tested within the research project, a 5-blade wind turbine and a 3-blade wind turbine. In general, the maximum power that can be obtained from a wind turbine is only 59% of the available wind power. As this general equation shows, Cp is called the power coefficient of the wind turbine. The theoretical maximum value of Cp coefficient is only 59%. This value is known as the Betz limit and represents the maximum power extraction efficiency of a wind turbine. In practice, a significant lower value can be achieved. The aerodynamic efficiency of a wind turbine, while converting the power available from the wind into mechanical power, is described by its power coefficient curve, Cp curve. The physical meaning of the Cp is the ratio of the actual power delivered by the turbine to the theoretical power available from the wind. The power coefficient Cp is not constant. It is actually a function of two variables, the tip speed ratio lambda and the rotor blade pitch angle beta. On the other hand, lambda depends on the rotor speed omega expressed in radians per second, the wind speed v expressed in meters per second, and the length of the turbine blade r, which is a constant. For low power fixed pitch wind turbines, the power coefficient depends only on the tip speed ratio. Using the relation between the available wind power Pw and the wind turbine power Pwt, the equation of the wind turbine power can be written in this way. The wind turbine torque is obtained from the wind turbine power divided by the rotor rotation speed omega. Another equation can be obtained for the torque if the power coefficient Cp is replaced by the torque coefficient Ct multiplied by lambda. The basic characteristics of the 5-blade wind turbine tested during the project implementation are presented in this slide. The wind turbine was designed for a rated power of 5.5 kilowatts and a rated wind speed of 11 meters per second. The maximum shaft rotation speed is approximately 126 rpm. The calculated wind turbine moment of inertia is 140 kg square meter. For a blade of 2.5 meters length, the blade swept area is 19.6 square meters. The curve of the power coefficient Cp versus the tip speed ratio lambda for the 5-blade fixed-pitch wind turbine shows that the maximum value of Cp is 0.42 at a tip speed ratio of 3. The equation for the torque coefficient Ct shown on this slide was obtained during the project implementation. This slide presents a family of power characteristics of the 5-blade wind turbine. Each curve, drawn for a constant wind speed, has an optimum value of the shaft rotation speed, for which the power given by the wind turbine is maximum. Connecting the optimal energy conversion power points of these curves that are drawn in blue, the optimal regimes characteristic is obtained. It is the green curve, which can be used for a simple control implementation to keep the operation at the maximum power point. If the maximum torque is needed, not the maximum power, this set of wind turbine torque characteristics can be used. The optimal points are obtained at different shaft rotation speeds than for the wind turbine power. For example, for a wind speed of 10 meters per second, the optimal value of omega for the torque characteristic is below 10 radians per second, while the optimal point for the power characteristic for 10 meters per second is 12 radians per second. In the first section, the wind speed is smaller than the cut-in speed, and so the extracted power is not enough to operate normally. The second section is called partial load. The wind speed is higher than the cut-in speed, and it is lower than the rated speed. The turbine starts to operate normally when the wind speed exceeds the cut-in speed. The tip-speed ratio is kept constant at the level which gives the maximum power coefficient, Cp, so the efficiency of the turbine is increased. In the third section, the wind speed is lower than the safe range limit, which is the cut-out speed, and higher than the rated speed. The objective is to maintain the rated output power by using one of the multiple power control solutions. In the fourth section, the wind speed is beyond the safe operation zone. The rotor will be braked, and the extracted power will be zero. Cut-in speed, rated speed, and cut-out speed are part of the specifications of a wind turbine. The characteristics of the three-blade wind turbine tested during the research project implementation are summarized in this slide. I will highlight the differences between the two turbines. The rated power is equal to that of the 5-blade wind turbine, while the rated wind speed is lower, 8 instead of 11 meters per second. This means that the 3-blade wind turbine is more suitable for places where the wind speed has usually moderate values. There are a lot of such places in our country. The maximum shaft rotation speed is 85 rpm, much lower than the maximum value of the 5-blade wind turbine. On the other hand, the blade has 3.5 meters. It is 1 meter longer than that of the other wind turbine. The blade swept area is double. It is 38.48 square meters in comparison to 19.6. The curve of the power coefficient Cp is similar to that for the 5-blade turbine. However, a slight increasing in the maximum value can be noticed from 0.42 to 0.46. Another difference between the two wind turbines can be mentioned. For the 3-blade turbine, the optimal value of the tip-speed ratio is 4, not 3. Finally, the torque coefficient Ct can be modeled by the same equation, but with different values for A, B, and Ct0 coefficients. The family of power characteristics of the 3-blade wind turbine is presented in this slide, starting from the power curve for wind speed of 5 meters per second, with increments of 1 meter per second. The last curve is for 10 meters per second wind speed, even though the rated value of the wind speed is 8 meters per second for this turbine. The last two curves are given for comparison with the characteristics of the 5-blade turbine. As can be seen in the figure, the maximum power at 10 meters per second is close to 11 kilowatt, which is double the maximum value for the other turbine. The curves are similar to those of the 5-blade wind turbine, but with different values for maximum power and optimum shaft rotation speed. As with the other turbine, the optimal regime's characteristic is easy to model and therefore can be used for a simple control implementation designed to maintain operation at the maximum power point. These are the 3-blade wind turbine torque characteristics. They are similar to those of the 5-blade turbine. The electrical generator characteristics are important for the wind energy conversion system because they have an impact on the other components of the system. For example, the necessity to include a gearbox and the type of gearbox needed are determined by the rated speed, but also have impact on the stability of the system, as I will show later in this presentation. A permanent magnet synchronous generator was designed and built for the research project. To keep the rated speed at a low value, the number of pole pairs was increased. PMSG is a standard synchronous machine where the DC excitation circuit is replaced with permanent magnets mounted on the rotor surface. Thus, the electrical losses in the rotor are eliminated and the thermal characteristics of the machine are improved. Also, the absence of the mechanical components such as brushes and slip rings makes the machine lighter, having a smaller physical size, a low moment of inertia, a higher power-to-weight ratio, a higher efficiency and reliability. Due to these advantages, the permanent magnet synchronous generator is an attractive solution for wind turbine applications. The main disadvantages of the permanent magnet excitation are high costs of the permanent magnets and the fixed excitation. Because PMSG is a surface-mounted magnet type generator and the permeability of the magnets is close to the air permeability, the inductances in the D and Q axes are equal and the synchronous inductance is defined as Ls is equal to Lq and equal to Ld. The main generator data are: the rated power is 5 kV amps, the rated current is 12 amps, the rated speed is 120 rpm, the rated frequency is 32 Hz. The generator has 33 stator slots. The number of pole pairs is 16, and the generator was designed with a permanent magnet flux of 1.32 Weber. PMSG was tested in unloaded condition using an AC variable speed DTC drive that included a motor mechanical coupled with the generator. This slide shows the experiment data obtained during no-load testing. The points represent the measured value of PMSG phase voltage at different shaft rotation speeds, and the line was obtained by least square linear regression. The same experimental setup was used to obtain the curve of the PMSG phase voltage for phase current variation up to the rated value of 12 amps. The generator was loaded in AC, not in DC. A three-phase variable resistor was used as load. The speed was held constant at the nominal value of 120 rpm. The phase voltage, phase current, and output active power were measured and recorded using a commercial power analyzer. This slide presents the PMSG efficiency curves versus phase current and output power respectively. The generated output power was calculated from the measured data of phase voltage and current. The input power, which is actually the mechanical power of the shaft, was calculated from the torque data acquired using a commercial torque transducer and shaft rotation speed data acquired using a speed transducer. The maximum efficiency is above 90%. A decrease of efficiency can be seen at low and high loads. At rated phase current, it is slightly above 85%. The values could be affected by measurement errors, but we did not calculate the exact impact of these errors on the values, as the main target was the proof of concept. Honestly, we consider that an improvement in the generated efficiency is possible, but this task requires a separate investigation focused only on optimizing the generator design. It may be a future work idea. This slide shows the same efficiency curves for a shaft rotation speed of 60 rpm. They were obtained using the same procedure, with the shaft rotation speed regulated at a constant value of 60 rpm by controlling the AC electric drive. The power in this case is limited to 2.5 kW, where the rated phase current is already reached. The efficiency is slightly higher than that for the nominal speed. This can be noticed especially in the first part of each curve. These are the curves for an intermediate value of the shaft rotation speed, 80 rpm. The efficiency is above 90% except for the last point. It is interesting to note that the efficiency does not drop below 87.5% even at the maximum phase current. The generated output power is limited to about 3.6 kW at this shaft speed. I have presented some of the efficiency data we obtain at different shaft speeds. Through extensive efficiency measurement, we have demonstrated that the permanent magnet synchronous generator, which was designed for the research project, is well suited for wind energy conversion for a wide range of operation. The power injected into the supercapacitor is smaller than the output power of the PMSG due to the losses in the three-phase diode bridge and hybrid DC-DC converter. The overall efficiency that takes into account all these losses is between 0.8 and 0.85, as can be seen in this slide. Generator efficiency is shown on the left for comparison. Therefore, a total of 15 to 20% of the input power, I mean the mechanical power at the shaft, can be lost in the process of conversion to electrical power at constant shaft rotation speed of 80 rpm. The same two curves are presented in this slide for a constant shaft rotation speed of 100 rpm. A suitable synchronous generator model is required to perform the digital simulation of the wind energy conversion and storage system. The model must take into account the specifics of the generator operation with a three-phase rectifier connected to the output. This model is different from the commonly used model of a three-phase synchronous generator. The reason is that, in most cases, the generator is connected not to an almost constant DC voltage filtered by the capacitor connected to the diode bridge output, but to a three-phase back-to-back converter that is responsible for injecting the power taking from the generator into the AC grid. Therefore, the PMSG model includes also the three-phase rectifier model. The equations of a simplified model presented in the literature are shown in this slide. This slide presents the PMSG model implementation in MATLAB Simulink. The DC voltage across the output capacitor VDC, which is the input voltage of the hybrid converter, the generator input and output powers, the generator torque, The rectified current IDC and the generator efficiency eta are the outputs of the model. The model for dynamic equation of motion was added to this block diagram. All the digital simulations carried on to test the WEX system used this generator model. To eliminate the speed sensor needed for control and performances evaluation, a generator rotation speed estimator was designed and implemented. The estimator is based on the measured PMSG rectified DC voltage and current, VDC and IDC. The figure on the left shows the equivalent circuit used for rotation speed estimation. dBr is the three-phase diode bridge, CF is the filter capacitance at the bridge output or the hybrid converter input, and RDC and LDC are the equivalent internal impedance components. The shaft rotation speed, omega, can be obtained from the equation written for the equivalent circuit, where the no-load output voltage can be expressed by multiplying the rotation speed by a constant, KDC, whose value was determined from no-load measurements. Using also the values of DC equivalent resistance, RDC, and DC equivalent inductance, LDC, the equation of omega shown on the right was obtained. If the values of DC voltage and current are known by measurement or by digital simulation, the rotation speed of the generator can be estimated. The figure on the right shows that this estimate is very accurate, the difference between the measured values and the estimated values being very small. A unidirectional hybrid switched inductor DC-DC converter is used to transfer the energy from the permanent magnet synchronous generator to the supercapacitor. This chapter presents a comprehensive analysis of this converter, considering the specific aspects of the small power wind energy conversion system. This analysis is necessary because the operation can become unstable if the stability is not correctly evaluated by taking into consideration the parameters of the electric generator. In addition, in energy conversion systems that contain supercapacitors, as in this application, it must also be taken into account that the converter must operate for a large variation of the output voltage. The main goal of a wind energy conversion system is to get the maximum available power from the wind turbine at each moment. This is done by loading the electrical generator in accordance with the wind speed, in order to keep the operation on the maximum power point of the wind turbine power speed characteristic. For medium and high power wind energy applications, back-to-back three-phase converter topologies are used to transfer the power from the wind turbine to the grid, while at the same time providing reactive and active power control. On the other hand, for low-power turbines up to 10 kW, the use of three-phase controlled rectifiers is generally considered too expensive. In these cases, the three-phase output voltage of the electric generator is rectified by a diode bridge, and a DC-DC converter is used to set the generator output power. A classical boost converter is suitable for this application if the converter output voltage bus is connected to an inverter, which transfers the power to the local grid. In small power wind energy conversion systems with energy storage elements, supercapacitors and/or batteries, The step-down converter topologies are more convenient to use because the number of storage cells in series, in this case, can be much lower. Hybrid DC-DC converters are good candidates for this application. HSI DC schematic is presented in this slide. For the sake of simplicity, I will present the converter operation and main equations considering the input voltage given by a DC source, not by a rectified sinusoidal voltage source. The converter current waveforms and the basic equations are the same in this case as in the case when a rectified three-phase sinusoidal voltage source is connected at the converter input. The influence of PMSG on the converter input current waveforms and system stability will be discussed later in this presentation. This type of hybrid converter is obtained by inserting a step-down switched inductor cell into the structure of a classical buck converter, as can be seen in the schematic. The inductors L1 and L2 are considered of equal inductance values. In consequence, the current waveforms are identical. In addition, the analysis requires the power switches S1, D1, and D2 to be ideal. In continuous current mode operation, the converter can be in one of the two possible states presented below the schematic. If S1 is in conduction, the inductors L1 and L2 are connected in series, and the energy is accumulated in their magnetic field. The voltage across one inductor is half of the difference between input and output voltages and is always positive. The current through L1 is rising linearly. In this state, the voltage across the output capacitor is rising, however, Cout is considered sufficiently large as the output voltage ripple can be neglected. The current Iout is equal to the inductor current. If S1 is blocked, L1 and L2 are connected in parallel through D1 and D2 diodes. The voltage across one inductor is negative, equal in absolute value to the output voltage. The inductor current is decreasing linearly and the part of the energy from its magnetic field is transferred to the converter output. Iout doubles its value at the instant when the diodes switch in conduction mode. The maximum value of Iout is twice the maximum inductor current, and its minimum is equal to the minimum inductor current. The AC component of Iout waveform is filtered by the output capacitor, and the DC component sets the output voltage applied across Rout. Of course, if instead of the resistance Rout, energy storage elements are connected to the output, as in the wind energy conversion as storage application, the converter output voltage is set by them. The current denoted Iout represents the charging current. However, the validity of the facts presented in this CCM analysis is preserved. The voltage conversion ratio, M, characteristic for HSI-DC operating in CCM, is obtained by applying the voltage second balance across one inductor. The equation of M shows that the output voltage is always lower than the input voltage. It is a mathematical proof that this hybrid converter is a step-down type. Due to the 2 - D term In the denominator, its voltage conversion ratio is reduced by up to 2 times compared to a classical buck converter, which is an advantage of the hybrid converter. The duty cycle of S1 in CCM can be expressed by this equation. The voltage stresses of transistors and diodes are given by these two equations. These are the characteristic current waveforms for the hybrid switched inductor converter for CCM operation. The inductor current is equal to the transistor current and to the output current I out while the transistor is on. On the other hand, while the transistor is off, the output current is 2 times higher than the input current. From these waveforms, a very simple relation between the average inductor current and the input current, I in, can be obtained. Because the input current is actually the load current for the electrical generator, this equation can be used for system control design if the converter operation is maintained in continuous conduction mode. In this case, the control variable can be the inductor current, and the equation can be used to calculate in real time the average inductor current that has to be regulated at each time instant using the values of the required input current and the duty cycle. The first choice as a control variable is the transistor current, because at each moment in continuous but also in discontinuous conduction mode, the average transistor current is equal to the input current. However, the transistor current goes to zero at each turn-off moment, having a very high derivative, in opposite to the input current. Due to this fact, sometimes it is easier to obtain the average value from the inductor current waveform than from the transistor current waveform. Therefore, the average inductor current could be a good candidate for the control variable. The switch current stress is always equal to the maximum inductor current, but can be expressed in relation to the required input current, the duty cycle, and the input and output voltages. The maximum switch current stress can be determined using this equation in the most unfavorable operating condition. A comparison between HSIDC and other topologies, including the classical buck converter, regarding the number of active and passive components, the voltage conversion ratio, and the transistor maximum voltage stress is presented in this table. Each of these topologies has only one transistor apart from the ID, which contains two. ID, and H2SC are hybrid topologies as HSIDC. They incorporate standard switched capacitor or switched inductor structures as defined in the literature. FOSDC and BBWCC make use of other passive switching structures. Apart from all the other converters from the table, BBWCC has also step-up capability. In addition, it allows the stacking of multiple passive switching structures at the output. However, only the one-stage BBWCC topology is listed in this table because the multiple stages topologies have worsened characteristics in regard to the application of wind energy conversion and storage. In comparison with the classical buck converter, HSI-DC has only two additional components, which is the smallest number from all the converters listed in the table. The maximum voltage stress of S1 switch is always higher for HSI-DC than for buck and ID converters. The comparison between HSI-DC and the other topologies in this aspect depends on the operating condition through D, the duty cycle. It can be seen that for HSI-DC, as the ratio between the output and input voltages is decreasing, the contribution of Vout in the S1 voltage stress is also decreasing, reducing the maximum value of the voltage across S1. Voltage conversion ratios of the converters listed in the previous table, plotted against duty cycle D, can be seen in this figure. A topology with a higher value of D at the given M has better performances for the presented WEX application. ID and BBWCC converters have lower duty cycles than buck. Therefore, their use is not convenient for WEX. ID-ID topology presents a duty cycle comparable with that of HSI-DC at low M, but it has many additional components, including a second transistor. H2SC converter has a higher D than HSI-DC, but it needs 6 more components. FOS-DC topology can be a competitor of HSI-DC for low-power WEX applications because it has a higher duty cycle than HSI-DC for M below 0.3. However, one diode and one capacitor are additionally needed for FOS-DC. Therefore, for step-down applications which do not require a very high decrease in voltage conversion ratio, the hybrid switched inductor DC-DC converter is more suitable due to the reduced number of components. Using HSI-DC instead of buck converter in small power WEX applications allows a significant increase in the duty cycle. For M equal 0.1 and M equal 0.2, D is higher with 82 and 66% respectively for the hybrid converter. An increased value of D can have a positive impact on the RMS transistor current. A further comparison between buck and HSI-DC converter is beneficial. The mathematical expressions of RMS average and peak values of S1 current for buck and HSI-DC converters are listed in this table. An increased value of D can have a positive impact on the RMS transistor current. Considering that the two converters operate at the same M required by the application, the RMS current of HSI-DC converter is 26% lower for M equal 0.1 and 22% lower for M equal 0.2. This reduction contributes to the efficiency improvement due to the decreasing of the conduction losses. On the other hand, the average transistor current is the same for HSI-DC and buck converters because it is equal to the average input current, which sets the PMSG and wind turbine operating points. Regarding the peak value of the transistor current, the reduction is much more pronounced than in the case of the RMS current. The first term in each equation is half of the inductor current ripple, which is supposed to be comparable in value for HSI-DC and buck converters because this ripple, expressed as a percent of the maximum inductor current, is imposed at the beginning of the inductor design. Therefore, considering only the second term of the equation for comparison, the HSI-DC transistor current peak value is reduced with 45% for M equals 0.1 and with 40% for M equals 0.2. This significant drop contributes to the efficiency improvement due to the decrease of the transistor current values at switch on and switch off moments, which results in the switching losses reduction. Even though HSI-DC has two extra components, it is a better alternative than buck converter for applications with moderate to high voltage conversion ratio due to the advantages already mentioned. For lower values than 0.1 for M, even if the HSI-DC converter can be used, it has a duty cycle of 10% at M equals 0.05, and other converters can be more suitable, for example FOS-DC. In this continuous conduction mode, all the energy accumulated in inductors during T-on is transferred to the load when the transistor is off. There is also a time interval with zero inductor current. The waveforms of transistor current, inductor current, and output current for a typical situation of DCM are presented in this slide. The time interval in which S1 is off is divided in two parts. In T of 1, the inductor current is positive and is linearly decreasing, and in T of 2, it is 0. The inductor current is greater than 0 in TL equal T on plus T of 1. The input current I in is equal to the average transistor current as in the case of continuous conduction mode. However, in this case, the maximum transistor current can also be used to calculate the input current if the duty cycle D is known. On the other hand, the maximum transistor current can be obtained from the input current at a given duty cycle. The equation of the average inductor current shows that its value does not depend on D, but on I in, V in, and V out. The relation between IL average and I in is the same in CCM and DCM. This can be a relevant aspect for control implementation if the converter switches from one mode to the other during operation. In DCM, the duty cycle is automatically controlled at the value expressed by the equation shown in this slide, in which instantaneous input and output voltages are imposed by application and the average input current is required by the wind turbine maximum power point tracking algorithm, MPPT. Please note that in this case of supercapacitor energy storage, the output voltage may change significantly during operation. The voltage conversion ratio at a known value of the duty cycle is given by a relation that is very different than that for CCM. At the CCM limit, or in other words, at the boundary between DCM and CCM, where the inductor current is zero in only one point, the input current has this mathematical form. If the average input current falls below this value of I in limit, the operation switches to discontinuous current mode. The three-dimensional surface presented in this slide was obtained for the limit value of the input current I in limit in V in and V out allowed ranges, which are 120 to 400 volt for input and 40 to 120 volt for output. There is a large variation or I in limit from less than 2 amps to more than 7 amps. The highest value corresponds to the operating point with V in equal 400 volt, which means a significant power level is needed at the converter input to guarantee CCM operation. In addition, I in limit does not decrease below 6 amps if V in is in the range of 200 to 400 volt and V out is close to its maximum. Thus, the optimum power point for PMSG can often require an I in below the three-dimensional surface. Therefore, the converter has to be able to sustain a stable operation in both continuous and discontinuous current modes. The WEX system contains two frequency-separated subsystems: the wind turbine, the mechanical subsystem with the slow time constant, and the electrical subsystem with the fast time constant. Therefore, under normal operating conditions, the mechanical subsystem has practically no influence on the electrical subsystem. The converter input current is regulated by a controller with the current reference given by a MPPT method. The controller has to provide stability for any PMSG loading condition. In general, during our research activity related to hybrid DC-DC converters, we have used until now three different methods to evaluate the stability: a mathematical method called state-space averaging, a circuit method called PWM switch method, and a digital simulation method. For a WEX application, we focused on the first two methods. I will present all the relevant information about the application of these methods on the unidirectional hybrid switched inductor DC-DC converter used in a small power wind energy conversion and storage system. Regarding the third method, it is based on the digital simulated response of the converter to a small amplitude AC excitation signal with frequency that is swept over the domain of interest. We used it in PSIM and LT-SPI simulators. State space averaging, or SSA for short, is a classical analytical method used for stability analysis of switching power converters. It is based on a continuous time average mathematical model of the converter. This is actually an equivalent model of the converter that has to be obtained. Usually, in the case of a DC-DC converter analysis, SSA is applied for the converter supplied by a DC source, which is not possible for HSI-DC use in the wind energy conversion and storage system. A DC equivalent model of PMSG is necessary because the electrical generator can have an important impact on stability. The schematic for stability analysis that contain the HSI DC converter with parasitic elements and the DC equivalent model of PMSG is presented in this slide. The assembly comprising the electrical generator and the diode bridge used to supply the converter was replaced by a DC equivalent model containing the voltage source VG, the equivalent inductance LG, and the equivalent resistance RLG. During operation, depending on the wind speed, VG varies between 130 and 400 volt. The values of LG and RLG components, which have an important influence on the system frequency behavior, were calculated from the PMSG parameters determined by experimental methods. All the operating states of a switching period contribute in a weighted way depending on the time interval for each state. The SSA method can be applied conveniently for continuous current mode. Its application in DCM is not suitable because it is necessary to take into consideration the additional state that appears in DCM, and thus a completely different equivalent average model of the converter is obtained for DCM. These are the equivalent circuits for T-on and T-off states used to obtain the equivalent average model of the converter by using the SSA method. The following hypotheses are considered valid for stability analysis. The power switching devices S1, D1, and D2 are ideal. VG and Vout, or VCS, have constant values during one switching period T. L1 and L2 have equal inductance values, and the series resistances RL1 and RL2 are also equal. Cin has an equivalent series resistance Rcin. There are three states variables defined in the following way. X1, the current through LG, which is also the converter input current, In. X2, the voltage across Cin. And X3, the current through L1. X3 is also equal to L2 current because L1 is equal to L2. What is interesting to note about these equivalent circuits is that no capacitor with its parasitic resistance is connected to the output, as is normally the case in stability analysis of DC-DC converters. This is because we found by analytical investigations that the output capacitor of the hybrid converter, Cout, and its equivalent series resistance have a negligible influence on stability due to the very high value of the supercapacitor Cs. Moreover, it was found that the influence of the parasitic resistance of the supercapacitor can be neglected. The state and output equations for T-on and T-off and the matrices representing the equation system are given in this slide. The following notations are used. L is used instead of L1 and also instead of L2, and RL is used instead of RL1 and also instead of RL2. The control variable, which is also the output of the state space model, Y, is the S1 switch current. In T-on time interval, the current through S1 switch is equal to the inductor L1 current. In T-off time interval, or in T-off state, the current through S1 switch is 0. It can be seen that the parameters of the DC equivalent model of the synchronous generator, LG and RLG, appear in many places in A1, B1, A2, and B2 matrices. According to SSA method, the continuous time equivalent average model of the system is given by this matrix equation system, where matrices A, B, and C are obtained from A1, B1, C1, and A2, B2, C2 through weighted summation, presented in these equations. The final forms of A, B, and C are in the right part of this slide. For the state space equation system of the equivalent average model of the hybrid converter, given in the previous slide, the small signal transfer function of the output variable Y is in the form presented here, where x0 represents the steady state operating point for which the stability is evaluated, and these two quantities are the small variations of I(S1) and D. The equation of the small signal transfer function for our particular application can be written as a ratio of 2/3 degree polynomials. The figure in the slide is used to highlight the influence of the synchronous generator DC equivalent model on small signal transfer function G. The body diagram of G is represented in two situations for the same operating point. The operating point is ILG 10 amps, VG 300 volt, and VCS 60 volt. If the converter is supplied by a DC voltage source, the body diagram is the one plotted with continuous line, the blue line. Actually, this represents the own hybrid converter transfer function, when the control variable is the average value of the transistor current. This behavior is specific for the converter, not for the system. It doesn't contain the influence of the synchronous generator. The converter equivalent average model that is characterized by this frequency response, the blue line, is obtained from the system model described above by removing the first row and the first column from A1 and A2 matrices, the first row from B1 and B2 matrices, and the first element from C1 and C2 vectors. If the hybrid converter is supplied by the synchronous generator with a three-phase diode bridge, the body diagram follows the dashed line. Important differences between the two diagrams can be noted in low frequency range, as is expected due to the LG impact. Differences of the same type were observed for the other operating points in CCM. The G transfer function coefficients shown in this slide were obtained based on the terms of the calculation results, given by a symbolic mathematics package. Afterwards, these terms were grouped and simplified. The coefficients A0 to A3 and B0 to B3 are functions of the duty cycle D, which is present at different powers, and all the elements in the schematic adapted for the stability analysis. The component values, including those of the DC equivalent model of the generator, the parasitic elements, and the input and output voltages. The equation for the transfer function G, together with the coefficient equations, form a parameterized small signal transfer function of the control variable IS1 that can be used for any similar WEX to quickly obtain the customized transfer function based on which the system stability is evaluated. The body diagrams of G small signal transfer function for three operating points are shown in this slide. The input current is 10 amps, the output voltage is 60 volts, and the DC voltage of the synchronous generator DC equivalent model is 130 for the first diagram, 250 for the second diagram, and 400 volt for the third diagram. It can be seen that the magnitude is influenced by Vg at low frequencies, and the phase curve is affected by Vg variations in the frequency range between 10 and 100 Hz. Contrarily, in the range of 100 Hz to 1000 Hz, the magnitude and phase are almost insensitive to Vg change. This behavior was also noted for the other two variables which determine the steady-state operating point, ILG and VCS. Consequently, if the HSI DC controller is designed for a cutoff frequency between 100 and 1000 Hz, the stability is not compromised by the change of the operating point. This method was proposed in the literature as a way to obtain the equivalent average model of a power converter using a general-purpose electronic circuit simulation software like SPICE. The nonlinearity is treated exactly where it appears in the circuit, not globally, as in the case of SSA method. The number of power transistors in the circuit must be equal to that of diodes, because the PWM switch model is an equivalent average model for a transistor-diode pair. Therefore, in order to use this method for the hybrid DC-DC converter, a transistor should be introduced in the original circuit with the constraint that nothing will be changed in the converter operation, waveforms, and theory. The appropriate position for this insertion is in the bottom part of the schematic. The new circuit with an additional transistor is presented in this slide, already prepared for application of the PWM switch model method. S1 and S2 power switches are driven synchronously to guarantee the equivalence with the original schematic. An AC excitation signal is fed into the circuit in a specific way, and subsequently the body diagram is obtained by a standard AC analysis performed in SPICE. The particular procedure used for this purpose is presented in the literature. This figure shows the body diagram of the wind energy conversion system small signal transfer function obtained in SPICE using the system model presented in the previous slide. The SSA body diagram for the same operating point in CCM is also given in order to compare the two results. As can be seen, there is a small difference between the two diagrams, which means that the SPICE model based on PWM switch model can be used with confidence. One advantage of the PWM switch model method implemented in SPICE is that the same simulation model can be used for CCM or DCM to get the frequency characteristics of the small signal transfer function. The third body diagram, plotted with red line, was obtained for a DCM operating point. For ILG 2 amps, VG 300 volts, and VCS 60 volt. In addition, the same model can be used for transient analysis to obtain the time response of the average model of the system. Moreover, using the PWM switch model in an average model, smooth transition between CCM and DCM can be assured in transient simulations. This fact was proved in the literature. The magnitude and phase characteristics of the WEG's small signal transfer function can be totally different in DCM compared to CCM. In addition, the graphical relationship between body diagrams of small signal transfer functions for HSI-DC and WEGs can be modified in DCM. For DCM operation, unlike CCM operation, the body diagrams of HSI-DC and WEGs small signal transfer functions show irrelevant differences at all frequencies, as can be seen in this figure. In other words, the frequency response of the system, which also includes the DC equivalent model of the synchronous generator, is almost the same as the frequency response of the converter. Combining the information obtained through SSA and PWM switch model methods, the current controller can be designed and subsequently the WEG stability can be verified for any operating condition, CCM or DCM. The current controller was designed according to the K-factor method, starting from the body diagrams of the control variable in CCM, presented in the previous slide. After that, the stability was checked for DCM operation. The controller transfer function shown here provides a phase margin of 70 degrees at the cutting frequency of 1 kHz in CCM. The values of the parameters Kc, omega z, and omega p are the results of applying the design method. The Bode diagrams of the overall open-loop small signal transfer function for two operating points in CCM and DCM respectively are shown in this figure. Overall means here the WEG system plus the controller. The controller modifies the magnitude and phase characteristics in order to guarantee the stability of the system. What is interesting to note in DCM is the shifting of the cutoff frequency from 1 kHz to 100 Hz, which together with the phase margin of 100 degrees means a much slower response in the transistor average current settling than for CCM. Actually, this is not a problem for the WEG's application due to the slow time constant of the mechanical subsystem. The important point is that the stability is preserved in DCM, which is absolutely necessary. The figure on the left shows the HSI DC prototype mounted in an electrical enclosure together with electrical installation equipment. It was used for WEG's testing in laboratory. The permanent magnet synchronous generator can be seen on the right. It is a part of a wind turbine emulator that will be presented in detail in part 5 of this set of presentations. The emulator also contains a gearbox and an induction machine. The synchronous generator is identical with the generator used at the location where the real wind turbine was placed. Not shown in the picture is the AC-DTC frequency converter used to drive the induction machine in order to provide at the shaft the same torque as a wind turbine. Using the components of this experimental setup, extensive tests were carried on in the laboratory. It was proved and afterwards presented in scientific papers that the wind turbine emulator can be successfully employed for wind energy conversion and storage system testing in laboratory without a real wind turbine. HSI DC prototype data are listed in this table. These values were also used for stability analysis. The IGBT type transistor was preferred over the MOSFET type, mainly due to its robustness. More advanced IGBT transistors are commercially available today. Some system performance improvements can be made if one of them is used in WEG's application. The key waveforms for steady-state CCM operation are presented on the left side. They were obtained through digital simulation and through data acquisition from the prototype, respectively. The steady-state CCM operating point was characterized by an input current IN of 7 amps, an input voltage VIN of 190 volt, and an output voltage Vout of 60 volt. A good correspondence with the theoretical waveforms shown in a previous slide at the beginning of this chapter could be noticed for the inductor current, transistor current, and output current. The input current waveform is one specific to a three-phase rectified current. Although the frequency of I in is much lower than the switching frequency, in steady-state operation its average value is equal to the mean value of the switch current IS1. An important fact was noted that even in the case of a light imbalance, about 10 to 15% of the real PMSG phase inductances, which causes unequal phase currents, as this figure shows, the average value of the input current is kept constant. This shows that the control system is not sensitive to deviations of the synchronous generator parameters from the theoretical design values, which is a positive aspect of the solution. The same waveforms are shown on the right side for steady-state TCM operation, with input current IN of 1.8 amps, input voltage Vin of 190 volt, and output voltage Vout of 60 volt. The comments on the CCM case are valid in this case as well. The effect on IE current of a step change in IS1 average current reference is shown in this figure. The reference of the transistor average current is changed in one step from 3 amps to 9 amps. The filter formed by PMSG phase inductances and the input capacitor of the hybrid converter Cin causes latency in the input current In waveform. In 300 milliseconds, the input current is settled at the new value. Given the slow wind turbine dynamics, this value is acceptable for WEX applications. The inductor current and the transistor current are changing much quickly, as expected. The configuration of a wind turbine system and the design and implementation of its control strategy to track the maximum power point are the most important elements in achieving the goal of a high-performance wind energy conversion and storage system. To capture the maximum energy from the available wind energy, a maximum power point tracking control (MPPT control) is required in order to adjust the turbine rotation speed in real time according to the instantaneous wind speed, so that the tip speed ratio can be maintained at its optimal value. The purpose of the WEX control is to provide at each moment the input current reference of the DC hybrid converter. On the other hand, the purpose of the converter control is to bring the actual input current of the converter, which is also the load current of the synchronous generator, to the reference value given by the WEX control, without oscillations. In this way, the operating point of the electrical generator is always adjusted to keep the wind turbine system at its maximum power point. This chapter focuses on presenting two ways of implementing the WEX control: a simple control strategy that can be used if the characteristics of the wind turbine are known, and a fuzzy logic control strategy that does not require the knowledge of the wind turbine characteristics. If the wind turbine operates in steady state with constant wind speed, the operating point moves along a single characteristic. Theoretically, there is only one point that corresponds to the maximum power on this characteristic. In this slide, the wind turbine power characteristics for three constant wind speeds are presented. For each wind speed, there is a different rotation speed omega for maximum power point of that characteristic. If the wind speed is changed from V1 to V2, for example, to keep the wind turbine system at the maximum power point, the system control has to modify the synchronous generator loading, which is the hybrid converter input current, in order to raise the turbine rotation speed from omega 1 to omega 2. In this way, the operating point will move from P1 to P2. If the wind turbine characteristics are known, they can be stored in the memory of the digital control system and used to evaluate the wind turbine operation. One important disadvantage of the simple MPPT control is that it is sensitive to changes in parameters values. This slide presents the influence of the air density variation on the wind turbine power characteristic at constant wind speed of 10 meters per second. There is a high difference between the maximum power point for an air density of 1.14555 and that for an air density of 1.3413, approximate 20%. The optimal regimes characteristic, which is obtained by connecting all the maximum power points from zero wind speed characteristic to the maximum allowable wind speed characteristic, is also affected by the air density variation. However, there is also a good aspect of this simple control. As can be seen in the figure, if only one characteristic of the optimum regimes is used, any of the three characteristics, the operating point can be kept near the maximum power point, not exactly at the maximum power point. Of course, there is a power loss, but that can be acceptable for a simple WEX control that is easy to implement. This simple control requires the knowledge of the optimal regimes characteristic presented in the previous slide. The relevant equations can be seen here. The wind turbine power for any wind speed has the maximum value at the optimal value of the shaft rotation speed, omega optimal, for that power characteristic. On the other hand, that optimal value of omega is related to the optimal value of the tip speed ratio, lambda optimal. Introducing the optimal lambda and the corresponding power coefficient in the equation of the wind turbine power, a simpler relation is obtained for the wind turbine power at the maximum power point. This expression is valid for each wind speed. The wind turbine power at the maximum power point is obtained by multiplying the cubic speed of the optimal rotation speed of that characteristic by a constant, k. This is the equation of the optimal regimes characteristic. In the simple WEX control, the input current of the hybrid converter is controlled in such a way that the synchronous generator is always loaded in order to implement the equation of optimal regimes characteristic, ORC, thus keeping the operation at the maximum power point. For steady state operation, neglecting the losses, this method gives acceptable results. The simple WEX control was tested by performing extensive digital simulations and using a wind turbine emulator implemented in laboratory. The simulation setup includes the simulation model of the permanent magnet synchronous generator described previously, a simple average model of the hybrid DC-DC converter, and the mathematical model of the wind turbine torque, also presented before. The control block uses the optimum regimes characteristic equation to calculate the wind turbine power to be achieved, and incorporates a PI controller to obtain the reference value of the converter input current from the power error, which is the difference between the wind turbine power and the PMSG mechanical power. The experimental setup for laboratory tests is presented in this slide. A wind turbine emulator is used instead of the simulation model. The implementation of the emulator is described in detail in part 5 of this set of presentations. In a few words, a wind turbine emulator consists of two parts: a software subsystem which implements the mathematical model of the wind turbine, and a hardware subsystem or a physical assembly that provides static and dynamic characteristics similar to the actual wind turbine system. The two parts work together. They are interdependent. The structure of the emulator contains a D-space control board connected to a PC, a voltage source inverter with direct torque control DTC, and the three-phase induction machine IM. The GB gearbox connected to the induction motor must be of the same type as that mounted in the nacelle of the wind turbine system being emulated. The emulator control was implemented in MATLAB Simulink and runs in real time on the D-space control board. This sends the reference torque of the induction motor to the DTC inverter, which returns the instantaneous torque of the induction machine, TIM, and the rotational speed, omega IM, to the control board. The inverter has the task of bringing the torque at the induction motor shaft to the reference value received from D-space. The implementation of the simple WEX control was done with the same MATLAB Simulink software block as in the digital simulation. The simple WEX control method was tested for both wind turbines. The system response to step changes of the wind speed between 7 and 5 meters per second and vice versa is shown in this slide for the 5-blade wind turbine. The digital simulation data are in green, and the experimental data obtained in the laboratory using the wind turbine emulator are in black. The figure on the left shows the waveforms of wind speed, input current reference for the hybrid DC-DC converter, rotation speed omega, and synchronous generator power. The figure on the right shows the power trajectory plotted against the rotation speed omega and illustrates how the control method works. The two steady-state wind turbine power characteristics for wind speed of 5 and 7 meters per second are drawn in red. For the characteristic for 5 meters per second, only the relevant part for explanations is drawn. The simulated PMSG input mechanical power is drawn in green, PG simulation. while the same quantity experimentally obtained using the emulator is drawn in black, PG experiment. The power values were recorded during simulation and experimental tests performing. The wind speed is initially 7 meters per second and the simulated power point follows an upward trajectory until it reaches the maximum power point of the power characteristic of the wind turbine. After that, the operation is maintained in an almost steady-state regime. Very small power variations around the maximum power point can be seen in the figure. Regarding the experimental power data, a startup period is not shown in the figure because the physical system needs a longer time interval to start up and operate in similar parameters as the simulation. When the wind speed suddenly changes to 5 meters per second, the wind turbine power will jump on the lower power characteristic, while the rotation speed cannot change instantly. Therefore, a dynamic process is started and the wind turbine control acts to move the operating point on the power characteristic for 5 meters per second to achieve maximum power in this new situation. Although the two power trajectories in the dynamic process are not the same, both simulation and experimental data showed that the new maximum power point is quickly reached. When the wind speed increases back to 7 meters per second, the PG power and the rotation speed increase until the system reaches again the maximum power point. It can be observed that for some time intervals, the generator power is bigger or smaller than the wind turbine power due to the transience, when a part of the energy is stored in or released from the mechanical components in rotation, while the rotation speed is increasing or decreasing. The same waveforms are presented in this slide for the three-blade wind turbine. There is only one difference in the conditions for simulation and experimental tests. The wind speed step is 1, not 2 meters per second. The wind speed is changed from 7 to 6 and back to 7. A good correspondence between simulation and experimental data can be observed also for these waveforms. The comments on the waveforms and power trajectories from the 5-blade wind turbine are in principle valid for this turbine as well. The fuzzy logic control is able to extract the maximum available power from the wind by increasing or decreasing the rectified PMSG current, which is equal to the input current of the hybrid converter. Changing the PMSG current changes the PMSG torque, which will modify the rotation speed according to the dynamic equation of motion. If the wind turbine operates to the left of the maximum power point, the controller must decrease the reference current and, as a result, the rotation speed will increase. On the other hand, when the operating point is to the right of the maximum power point, the controller must increase the reference current to reduce the rotation speed to approach the optimal value of omega. The proposed fuzzy logic controller has three input variables: the change in the mechanical power delta PM, the change in the rotation speed delta omega and the sign of the ratio of delta Pm to delta omega. The output variable is the change in the reference value of PMSG rectified current, delta I. These input and output variables are normalized in the range -1, 1 to make the FLC block universal so that it can be implemented for other wind turbine systems. This requires the use of the scaling factors K omega and Kp at the controller input. The reference value of the PMSG rectified current is obtained by integration. The block diagram of the MATLAB Simulink simulation model of the wind energy conversion and storage system with fuzzy logic controller is presented in this slide. The simple MPPT controller block was replaced by the FLC block, while the other components of the model are the same as for the simple control simulation. Some technical details regarding fuzzy logic controller implementation are: the input and output variables are normalized in the range of -1 to +1. The FLC algorithm is characterized by if-then rules as shown in the following table. The rules are designed so that the controller always seeks a maximum power point without stopping. The output fuzzy sets are identified using the min-max fuzzy implication method. Simple triangular and trapezoidal membership functions are used for FLC implementation. The center of gravity or centroid defuzzification method was used to obtain the output variable. The fuzzy membership functions are n negative, ns negative small, z 0, ps positive small, and p positive. Fuzzy membership functions in red are for a positive derivative of Pm with respect to omega, and those in blue are for a negative derivative. The main characteristics of the MPPT fuzzy logic controller are: the controller compensates the steady-state turbine power curves in order to obtain the true maximum power that is available in transients. The fuzzy controller basic rules are derived from the desired system behavior and the designed control strategy and are different for the left side of the power omega curve than for the right side of the power omega curve. The rules are designed so that the controller always seeks a maximum power point without stopping. These simulation results for step changes of the wind speed between 7 and 10 meters per second and vice versa were recorded for the 5-blade wind turbine. Similar results were obtained for the 3-blade wind turbine. The waveforms are the wind speed, the reference current for the hybrid converter, the rotation speed omega, and the synchronous generator mechanical power. In the same figure, the mechanical power for simple MPPT control was plotted in green. The two waveforms overlap almost entirely. A small difference can be seen here. Due to the transient regime between the two steady-state operating conditions. Extensive simulation tests were performed. The simulation data show that the fuzzy logic controller can search and also track the maximum power point for any wind speed. The power trajectory plotted against the rotation speed omega illustrates how the fuzzy logic controller works. The two steady-state wind turbine power characteristics for wind turbine of 7 and 10 meters per second are drawn in red. The simulated PMSG input mechanical power is drawn in blue. The wind speed is initially 7 and the simulated power point follows an upward trajectory until it reaches the maximum power point. After that, the operation is maintained at the maximum power point with very small power variations that can be observed in the figure. When the wind speed suddenly changes to 10 meters per second, a dynamic process is started and the wind turbine control acts to move the operating point on the power characteristic for 10 meters per second to achieve maximum power. Compared to the same power trajectory recorded for the simple MPPT control, the results obtained for the fuzzy logic controller show a more direct way in which a new maximum power point is reached. To test the controller immunity to perturbations, the moment of inertia was decreased with 50%. The power trajectory is shown on the right for this case. The maximum power point operation is achieved, but in a different way. The operating point reaches the new power characteristic of the wind turbine at a significant distance from the optimal operating point and then moves along that characteristic to the maximum power point. If the moment of inertia is increased with 50%, the new optimal operating point is also reached. The power trajectory is directly to the new maximum power point. This figure shows the power versus rotation speed curves obtained with the fuzzy logic controller for different values of the torque coefficient Ct of the wind turbine for a wind speed of 10 meters per second. The original value of Ct was increased with 20% to obtain Ct1 and decreased with 20% to obtain Ct2. The results prove that the proposed controller is robust with respect to the changes in wind turbine system parameters and air density. The advantages of the fuzzy logic controller are robustness. It can be used even if the wind turbine speed parameters, wind turbine characteristics, or the wind speed are changing or are not well known. Simplicity and low computational cost of the FLC, designed considering only the necessary rules and associated fuzzy operators. The adaptation to another low-power wind energy conversion and storage system is straightforward. Real operating condition testing was done on a wind energy conversion and storage system identical with that tested in laboratory, but the generator was mechanically connected to a 5 kW wind turbine mounted at the top of a 15-meter tower. This is a picture of the place where the wind turbine and WEX are located. The hybrid converter is installed inside the metallic container located behind the tower in an electrical cabinet that contains also the supercapacitor, 4 12-volt batteries in series, a battery charge controller, an inverter that is used to provide a local AC grid because the grid is not available at that place, and the electrical equipment for connecting, monitoring and protection. The wind turbine system was monitored and supervised using a SCADA system which allows browser connection from distance. The waveforms and the important values can be displayed on the monitor of any internet-connected PC or laptop. Selected WEX data acquired through the local SCADA system are presented in this slide. They are the wind speed and the input power, voltage and current of the hybrid DC-DC converter. The input current, I-in, is controlled by HSI DC to keep the wind turbine at the maximum power point at each moment. The reference value of I-in is sent to HSI DC by the MPPT control block. An industrial programmable logic controller, PLC, was used to measure the relevant physical quantities, to calculate the I-in reference current, to coordinate the circuit protection devices, and to connect additional loads if the supercapacitor voltage Vout is too high. A scenario for supercapacitor voltage control is presented here in relation to experimental data. This was implemented in the programmable logic controller and worked well. It can be modified to suit different possible situations. The flexibility is very high. A sustained high or relatively high input power in the case of low total power consumption, which is the power consumed by loads and battery charging, leads to the increasing of the supercapacitor voltage up to 90 volt, which is one of the voltage control levels used in PLC. An additional load is connected when the supercapacitor voltage reaches 90 volt, and then the voltage decreases to 70 volt, which is the control level used for load disconnection. After the additional load is disconnected, the supercapacitor voltage increases again to 90 volt if the input power continues to be higher than the total consumed power. When the input power does not exceed the consumption demand, the output voltage of HSI DC is maintained at 60 volt by the DC battery charger, which is directly connected to the supercapacitor and uses its energy to charge the batteries. Conclusion. The presentation was focused on a small power wind energy conversion system where a hybrid switched inductor DC-DC converter has two roles: to maintain the wind turbine at the maximum power point by controlling the electrical generator loading, and to charge a high power density supercapacitor, which is part of a hybrid storage unit that also contains rechargeable batteries. The presented wind energy conversion and storage system is simple and can be used for small power wind turbine. It is an appropriate application for hybrid DC-DC converters. The stability has to be investigated with care due to the influence of the synchronous generator parameters. A parameterized small signal transfer function of the control variable described in this presentation can be used to quickly obtain the information needed to evaluate the stability of any similar wax. A simple MPPT control or a more elaborate fuzzy logic control can be used to calculate the reference value of the converter input current in order to achieve the maximum power point operation. FLC can be used even if the wind turbine system parameters, wind turbine characteristics, or air density are changing or unknown. All tests performed on the energy conversion and storage system through digital simulations or using a wind emulator, as well as tests performed under real operating conditions, confirmed the validity of the solution and that the hybrid switched inductor DC-DC converter is suitable for similar small power wind energy conversion systems. You can find additional information about the small power wind energy conversion and storage system in the papers from this list of selected references. In the end, I hope that at least a few ideas might be valuable for you. Thank you for watching. I wish you all the best.